All right, thank you all. So I will be talking today about an application that has important social impact, economic impact, namely land use predicting. And we're using HPC and DDN equipment to do it. But the majority of my talk will be about what is important, what are we doing with all this equipment and this HPC and the data analytics. So the problem is land use discussion. And everybody is sort of personally attached to this because it means in your city what is going to be done with different parcels of land. Is it going to be for single houses? Are you going to have industrial development? Is it a business? Is there going to be some traffic implication, roads? And these discussions used to be made by people who thought about it, had the best interest of everybody at mind, and then just made a decision. But as we now are moving in a more complicated society, more users and more communities are interested and have a personal stake. Like homeowners want to know what is going to happen to my neighborhood if right next door you're going to put something that is an industrial plant. And people want to have a discussion. Other people, like the stakeholders, you can see here a little table. You know, there is land use for, you want agricultural, livestock. We have special farms. There are nurseries for growing plants. They all have different implications. They have different smells, as people who know right next to a pork plant. Then there's a new thing that was never of concern 100 years ago. That is, we want to have a conversation about our whole ecology. And all these, and then the urban decisions of single family homes. Do you want everybody to have their little backyard, or do we want to have more compact apartment living that allows you to live without a car? You can go shopping and you can go out and you can have entertainment, and only if you want to go for the weekend a long time away, you move away. So all these decisions need to be made, and you need to come up with some data to inform the discussion. In the past, a city board or developers would make some negotiations, and then all kinds of stakeholders would basically left out. And even if you now bring them together, then people will have vague arguments about what will be the impact of putting more industry there or a bus station there. So the data that I'm going to talk to you about is from the Orange County, which is the county that Orlando is in. Everybody knows Orlando. Orlando has a big Disney World. It has a lot of international traffic because people come do tourism, but there's also a lot of agriculture. Of course, there is industry. There are people who have homes, they want to live there. One of the things that you have to look at is, where do we get our data? So we collect all kinds of data from the state, from the city, and we gather all of this. That will be used to inform our decision. In the end, we basically divide up the entire county in little parcels. And then these parcels, we have to sort of decide. Some parcels have really weird shapes, and that makes them very hard to make a decision about. They're sort of treated as exceptions. And that's where there's this thinness radius comes in. So if you have a parcel that is a little strip somewhere, that's not very meaningful. You want something that has a little bit of volume to it, a little bit of squareness. And so the thin ones get eliminated. So then what do? We now have the process of our research is to gather the data, and then there is this system. It is a land use decision and conflict information system where people would basically plug in all this information that they have, and then they would run for several hours in a model, and they would say, okay, this would be the impact of putting more single home houses in this parcel and less agriculture in that parcel, and so on. and then they would maybe, after a couple of weeks, they would have 5 or 10 different scenarios, and then they would have a meeting with all the stakeholders, which one is the best. What we want to do is use high-performance computing, turn this into a big data problem where we say, well, let's go and statistically generate hundreds of models so that we can see, well, if you vary it a little bit, what would be the impact on, say, traffic? Do we need another extra road if you're going to put something like an Amazon distribution center in the middle of your county? So the calculations were done on HyperGator, which is the University of Florida supercomputer. It has 30,000 Intel cores, 16,000 AMD cores. The storage system has 2 petabytes of a Dell Scratch system, then 3 petabytes of DDN storage, and right now, this week, being delivered is another 4 petabyte new storage system that's been optimized for exactly this kind of calculations. As people know, when you do this big data where you want to run machine learning and data deep learning with artificial intelligence type algorithms, you're going to have lots of little files. And the latest system here that we configured, that's being delivered now, has lots of firmware, sort of basically cache storage, and is really optimized for this performance. And then we use Mellanox interconnect to hook it all up. So then the problem of doing this is actually easily parallelizable, because what we want to do is we need to figure out all these parcels, calculate their interactions, and then we want to run many, many models. And that's what we can do on our computer. That's what we have done. So basically, going through, we figure out what the algorithm is, implement it in Python, and then we basically run a very large number of systems. And you can see here, one calculation on an SMP node takes from 44 to 48 minutes. And when we run it on the cluster, it takes 5 minutes for one simulation. And then we can run like 100 of them in parallel. So in 5 minutes, we have 100 different scenarios. Then we can basically extract the data where you create some indices. So I'm not going to go in detail of how this is done, but essentially there's some statistical analysis you do on the data to sort of extract what is the impact of one choice, so that we can come up with an optimal index of what is useful. And then you can basically see here, there's a couple of diagrams where you say, well, what is the impact of all these models for parcel number, and it gives a particular number here. And say, what if I use it for single home? And then you can see here, the single home use, in this particular case, is sort of an optimized index. And now you can basically have an argument with all the stakeholders, what is going to be the impact of multiple ways of implementing it, and from that you can pick the best. So you can sort of say the least impact on road traffic or noise or any of these things that are of concern to the different stakeholders are weighed against each other. And you can present the data in different ways and basically have an informed discussion when all these stakeholders come together, and that way people at the city and different developers and all kinds of negotiations with the state for funding on roads or other infrastructure can now be informed by this, because we can produce them or provide them with the data. So we think this is a very useful. Here is some more way of characterizing the numbers, and then in the end you can have overall view. So we do this for each parcel where we can help make the decision, and then we can also say, well, now when you look over all these models, what is going to be the impact on the total county, so that you can have an overall decision where you say, if we want to preserve some nature area, we want to make sure that there is large contiguous area, because then the conservation works better rather than having little sparsed out. And then this way you can sort of assemble all the answers about the different parcels and see, well, what would be the best for the whole county. And then everybody can make a better decision. So that's essentially my conversation or my presentation about land use and how computers, parallel storage, and high-performance computing can help everybody in the community make better decisions about how to move forward with the land that we have and that we want to use to the best possible way. Thank you.
Excellent. Thank you so much. Give them a round of applause. We love having our guest speakers. Thank you so much, Erik.